So now let's think about our capacitor, and let's start with a charged capacitor. It is fully charged, it is not discharging. And the reason it's not discharging is because we haven't actually connected two plates with a wire. Notice that there's a gap here. And in general, we don't let charges just leap through the air, right? That doesn't typically happen unless there's a spark, which we only talk about when we're explicitly talking about the spark. So in this case, we actually do have electrostatic equilibrium. Why? Because all of our charges are stationary, and that means that all of our surface charges are more or less uniformly distributed. And, well, through our conductors, right? Because this is a conducting wire. And that means that our electric field inside the conductor is zero. So this is our situation from like chapter 23, chapter 24. So this is what we used to talk about. So we would say that we have a negative plate and a positive plate of our capacitor, but since it's connected to this conductor, these negative charges are also distributed along that conductor as a surface charge density, because it's a conductor in electrostatic equilibrium. Same thing on the positive side, that we've distributed those positive charges, again, as a surface charge density, because this is a conductor. And at every single point inside the wire, we have zero electric field. No charges are moving, they're all stationary. Again, equilibrium. So right now, this is a charged capacitor. It is not discharging because there's a gap. So what we then want to think about is what is going to happen when we actually close that gap. For instance, by closing a switch. What is then going to happen? Well, most importantly, you no longer have electrostatic equilibrium. This is just not true. This is now discharging, which means that you have moving charges and you have your electric field in your conductor. So this is really important. So our electric field is now being caused by those variation in surface charge densities, right? So you can think in a way of in the center region, now that these charges have been able to equalize first, we have less surface charge density here than we do in other regions. And as this decreases in surface charge density, we can actually keep pulling, again, technically it's electrons moving, but positive charges off. Here, as again, this decreases in surface charge density, there are free electrons that can keep coming over. So what we see is that we have this electric field that is causing charges to move. And, again, it's being caused by variations in our surface charge density. Here it's very negative, here it's slightly less negative, neutral, positive, more positive, very positive. And again, once you have those variations in surface charge density, you get an electric field. Now, obviously the electric field here is changing direction because our wire is bendy, and we haven't argued that it's actually a uniform electric field, but that's actually a minor thing. Right now we're just trying to understand why charges are moving in our wire. So that's the basics of why and how we create current. We're now going to zoom in and think about that microscopic level and try to relate this big picture and electric fields back to our electron current.